Good morning, everyone. I am Daniel Tenorio, and I'm going to present Lee's algorithm for maze routing. The outline of this presentation, I'm going to start with an introduction, the current usage, an implementation, and the proposed solution. Have you ever imagined yourself being stuck in a maze? You wonder how can you find your way out with all the tall obstacles blocking you? I bet if that happens, you'll only wish you have something in your hand that can help you easily find a way out. But first, let me just define what a maze is. A maze is a puzzle with a starting point and exit point. It has one way in and one way out. But before you reach the exit point, there are many different paths you need to take, and a wrong choice of path might result to a dead end. Just a trivia, a maze is different with a labyrinth. The labyrinth has only one way in and out, meaning its entry point is also the exit point. From these two illustrations, I hope you are able to determine which is a maze and which is a labyrinth. Maze routing algorithms are widely used in VLSI or Very Large Scale Integration Design. It is used in computer-aided systems to route wires on printed circuit dashboard. It is also used to address the problem of finding the shortest path from a source to the destination and avoiding obstacles in AI-designed computer games, especially for the agent or character movement. Another implementation of this algorithm is for mobile robot path. It is applied to get the shortest collision-free path of the mobile robot. It also makes the mobile robot capable to rotate and avoid the blockers ahead of it in order to pass the passage intelligently. There are different maze routing algorithms today, like Lee's algorithm. It is a single layer routing that is based on a breadth first search. Then we have Sokoop's algorithm. It is a combination of a breadth first and depth first search, and it's faster than Lee's algorithm. Next, we have Hadlock's algorithm, a shortest path algorithm used for grid graphs. Next, we have Mikami Tabuchi's algorithm. It is an algorithm where every grid point is an escape point. Lastly, we have Hightower's algorithm, where a single escape point is placed on each line segment that just passed the endpoint of the segment. With all these algorithms I've mentioned, we will be focusing on Lee's algorithm implementation in maze routing. According to Wikipedia, a maze runner is a connection routing method that represents the entire routing space as a grid, and some parts of it are blocked by some components. The goal is to find a way from point A to point B. We cannot go over or through these blocked cells. From point A, we need to calculate the minimum number of steps required to reach point B without moving diagonally. The only possible moves are up, down, left, and right. It uses a wave propagation style throughout the dense layout until it reaches its destination. One of the simplest and easy solutions of solving maze routing is Lee's algorithm. It is based on breadth first search, and it always gives an optimal solution if there is a connection between two endpoints, and can guarantee to return the minimum path taken. But an issue with this algorithm is that it is slow and requires a considerable amount of memory for a solid layout. Here is the pseudocode for Lee's algorithm. First, we initialize the starting point with 0. Then, the next step, this is where the propagation happens. We mark unlabeled neighbors with 1 and repeat it by adding 1 to the neighbors of the previous labeled mark until we reach our target, or there's no more points to be marked. The third step, this is the part of backtracking. We go to our target point where we will begin our process this time. We go to the next node which has a lower point than the current node. I repeat this until we reach the start point. Lastly, clear all marks after we find the short minimum path. Maybe it would be better to discuss it with some illustrations. Here in figure 1, we first identify our starting point and target point. Then in figure 2, this shows the first step where all neighbor points of S moving up, down, left, and right are set to 1. This indicates that the shortest distances are equal to 1. In figure 3, we then consider all neighboring points of label 1 and increment their labels with 1, giving us now 2. This indicates that these are now the shortest distances from our starting point. This propagation continues and goes on and on until we reach our target point, which you can see in figure 4. We have reached our target point and we will now backtrack for the minimum path. In figure 5, we start with the target point and move to any neighboring point with a label 1 less than the current label point. The procedure continues until we reach the starting point. I'll just take note that there are several possible directions the path can go to, and this will vary with the weights of the cells in the graph. Lee's algorithm has high complexity, especially if we are dealing with a very large grid size. Also, take a look how much computation we had just to reach the endpoint. So here in the proposed solution, Lee's algorithm can be minimized by initiating the computation from both the starting point and target point, which you can see in figure 7. The process continues just how it propagates a while ago. Here in figure 8, you can see that both ends repeat the same process of labeling the neighbors of a label point with 1. Then in figure 9, we can see where the neighbors of both ends intersect, and that is where the backtracking will happen. With this kind of implementation of Lee's algorithm, it can give us a less time complexity result since we are not waiting from the start point to reach the target point. Instead, both ends propagate at the same time until they meet. This can also give us less wasteful computations because we are counting with the same distance numbers and not an incremental distance number from the start point only. Then here in figure 10, we will backtrack based on where both points intersect to find the minimum path. The result looks like the same as the previous example, maybe because the placement of the starting point and target point is within reach with no blockers. But hopefully, this will give a reasonable output once implemented. That's it for my presentation. Thank you everyone for listening. Have a nice day.